Hi, this is Sushma, working as Associate Professor in the Department of CSC. Now we are going to discuss about K-means clustering algorithm. As earlier we have discussed about what are the different types of clustering. This K-means clustering algorithm comes under the prototype-based clusters, and here this prototype based clustering techniques generally create one level partitioning of the data objects, and there are a number of such techniques, but two of the most important are k-means and k-mediod algorithms. And here we'll be discussing about a k-means algorithm which defines a prototype in terms of a centroid. Here the centroid is considered as the prototype to be followed here, which usually nothing but the mean of a group of points applied to the data objects in a continuous n-dimensional space. Here the centroid, what you will be considering is nothing but the mean value. As earlier we have discussed that mean is considered to be the centroid when you're considering the continuous attribute values. Here you'll be considering the continuous attribute values. In such continuous attribute values, mean is considered as the centroid. And coming to the algorithm of a basic k-means algorithm, here the first thing, what does k indicate here? K here indicates nothing but the initial centroid values. Here you will be considering k clusters. In order to consider design or k clusters, k initial centroids must be considered initially. Okay, and here you need to specify the number of clusters desired by the user. That is nothing but the k. Each point is then whatever the data objects or the data points that you are having, it is then assigned to the closest centroid, and each collection of points assigned to the centroid is nothing but the cluster. Okay, then the centroid of each cluster must be updated based on the points assigned to the cluster. When once the points are assigned to the cluster, each and every time the centroid must be updated, and this process must be repeated until the centroid value remains the same. And the same thing is discussed here in the algorithm. Initially the first step is select k points as initial centroids, and the process must be repeated until the centroids do not change. The process is you need to form the k clusters by assigning each point to its closest centroid, and you need to recompute the centroid every time a point is assigned to the cluster. This is the algorithm for basic k-means. And coming to, as we have discussed that you need to assign the points to the closest centroid. What is the, how to identify the closest centroid? That is nothing but the next topic that we'll be discussing, assigning the points to the closest centroid. In order to assign the points to the closest centroid, some proximity measure must be followed. Here the proximity measure is nothing but that which is used to quantify the closest for the specific data what you are considering. And here suppose if you are considering Euclidean space, the data points that are present in the Euclidean space. What do you mean by Euclidean space? It's nothing but the data which is represented either in one dimensional or two dimensional or three dimensional, any dimensional space. And here if you are considering the data point in the Euclidean space where it can be represented in the form of x comma y coordinate values, such data, the proximity measure can be calculated using the Euclidean distance. For the Euclidean space, one of the measure for proximity is nothing but Euclidean distance, and the other measure is Manhattan distance. And if you are considering the documented data, then the proximity measure what you can consider is cosine similarity is the first one, and the second one is Jacquard measure. And these are the different proximity measures what you will be using to calculate the distance of the points to the centroid. And the next what is nothing but centroids and their objective functions. As we have stated in the algorithm that we need to recompute the centroid of each cluster. Since the centroid may be varying depending on the proximity measure for the data and the goal of the clustering, Here, the main goal of clustering is nothing but typically expressed by an objective function. Here it is nothing but minimizing the square distance of the each point to its closest centroid. Here we are explaining this with the help of two types of data. What we are considering, one is the data in the Euclidean space and the data documented data. Suppose if you are considering the data in the Euclidean space, here our main objective function is nothing but which is measuring the quality of a clustering, which is nothing but here we will be using the SSC value, that is sum of squared errors, which is also known as scatter. Here, in other words, we can calculate the error of each data point, that is its Euclidean distance to the closest centroid, and then we need to compute the total sum of the squared errors. Given these two different set of clusters that are produced by two different runs of k-means, here we'll be generally preferring the one cluster with the smallest squared error value, since it means that the prototypes of the clustering are better representation of the points in their cluster. That means here you will be considering only the cluster having the smallest SSC value. Using this, here you will be representing the formula for SSC can be represented as SSC is equal to summation I is equal to 1 to K summation X belongs to Ci, capital Ci. Here you need to observe, and distance of Ci comma X whole square. Here distance is nothing but the general distance formula what you will be having, distance of Ci comma X whole square. And here where the value of X represents the object, capital Ci represents the ith cluster, and the small ci within the distance, it represents the centroid of the cluster Ci, and mi value is nothing but the number of objects in the ith cluster, and k value is the number of clusters. Okay, like this we will be calculating the SSC value for all the clusters, and the cluster which is having the least SSC value, the cluster with the smallest SSC value will be chosen. And suppose if the data what you are considering is not a Euclidean space data, and if it is a documented data, then the k-means is can be considered. We can consider the document data, and the cosine similarity measure can be applied here. Here we will be assuming that the document data is represented as a document term matrix. What do you mean by document term matrix? It is nothing but here you will be identifying what are the different terms that are present in all the documents, and along the columns you will be representing the document terms, and along the row values you will be representing the title of the documents, like document 1, document 2, and so on. And the values, the intersecting values of this column and the rows represent nothing but the how many times each term is represented in that particular document. And here our main objective is nothing but to maximize the similarity of the documents. Earlier we are trying to reduce the SSC value, but here we are trying to maximize the similarity of the documents that are present in a cluster to the cluster centroid. This quantity can be calculated by making use of total cohesion. Okay, and here the total cohesion can be calculated by making use of the formula given here, summation I equal to 1 to K summation X belongs to capital Ci cosine of X comma Ci, okay, which is used to calculate the cohesion value. And another step what you are having in the basic k-means algorithm is you need to choose the initial centroid value. When you are choosing the initial centroid value using a random selection, it doesn't result in very good clustering. Okay, here it results in a very poor clusters. Therefore, what you're trying to do is you're going for another technique where you will be choosing a group of points and cluster them by making use of the hierarchical clustering technique. And here the K clusters are extracted from the hierarchical clustering, and these centroids will be used as the initial centroids. By using hierarchical clustering, you will be identifying all the K clusters, and the centroids of all these K clusters are considered as the initial centroids. This is one technique, and the other one is you can choose the initial centroid randomly, and then uh, you can choose the next centroid which must be far away from the first centroid, and the third centroid must be chosen such that it is far away from the first and the second centroid. Like this we need to carry on until all the K centroids are identified. Hence now you have learned about uh, how to choose the initial centroids, how to calculate the proximity measure. That means you need to recompute the values. That recomputation can be done using the different ways. And the next one is choosing the proximity measure. When this and the next one is nothing but the time and space complexity for this K-means algorithm. And coming to the storage space that is required for this K-means algorithm is a big O of m plus k times of n. What is this m represents here? M here represents the number of points, and n represents the number of attributes. K or capital K is nothing but the K clusters, number of clusters, and the time that is required here is big O of I into K into M into N. Here I is nothing but, as you already know what is K, M and N. Okay, I is nothing but the number of iterations that are required for your generating this K-means algorithm. And apart from all these, some additional issues are there which must be handled by the K-means algorithm. And coming to those additional issues, the first additional issue that must be handled is you need to handle the empty clusters. The main problem that you will be having with the basic K-means algorithm is that empty clusters can be obtained if no points are allocated to a cluster. That means if you are not allocating any point to a cluster, then automatically empty clusters will be identified. If this happens, then you need a strategy which is needed to choose a replacement centroid. Otherwise the SSA value will be larger. Generally you need to reduce the SSA value, but here if as there will be the generation of empty clusters, the SSA value will be increased. And the one approach is to choose the point that is far away from any current centroid. You need to see that no empty clusters are identified. And the second issue what you have to identify here is outliers. That means when the squared error criteria is used, outliers can influence easily the clusters that are found. That is, in particular here, when outliers are present, the resulting cluster centroids may not be as representative as they are. That is, the SSC will be higher. If the outliers are there, their SSC value will also be higher, because of which it is often useful to discover the outliers, and we need to eliminate them earlier. Therefore, even the outliers must be handled by the K-means algorithm. And the next one what you're having is here you need to reduce the SSC value. How to reduce the SSC value? Okay, as I told earlier, always the SSC value must be minimum SSC value will be chosen. In order to do that, if here you will be using two strategies in order to reduce the SSC value by increasing the number of clusters. Here the SSC value will be reduced, but the number of clusters will be increased. Here there are two methods for that. One is splitting a cluster and the other one is introducing a new cluster centroid. What do you mean by splitting a cluster here? The cluster which is having the largest SSC value, we will be choosing that cluster, and we can split that cluster into one or more clusters, two or more clusters, such that when the number of data points are reduced, automatically the SSC value can be reduced. And the other one is introducing a new cluster centroid, and often that means here we can easily determine if we keep track of the SSC value by introducing a new cluster. Here you will be introducing a new cluster, and the data points from other cluster will be assigned to this new cluster. Thereby also we will be having the ability to reduce the SSC value. And another two strategies we are having here, which will also reduce the SSC value but by decreasing the number of clusters. Okay, those are disperse a cluster and merging the two clusters. Coming to the disperse of a cluster, here this can be accomplished by just removing the centroid which is corresponding to the cluster and reassigning the points to the other clusters. And the cluster that is dispersed should be the one that increases the total SSC. And here coming to the next one, that is merging of the two clusters. The clusters with the closest centroids will be chosen, and the approach is to merge the two clusters that result in the smallest increase in the total SSC. Now by using these two techniques we can reduce the SSC value, thereby the number of clusters will also be reduced. And here in order to overcome all these, here we are having an extension of the K-means algorithm, which is nothing but a bisecting K-means algorithm. And this bisecting K-means algorithm is a straightforward extension of the basic K-means algorithm, whose idea is to obtain K clusters by splitting the set of all points into two clusters initially, select one of these two clusters to split and again split them into two clusters, and this process must be repeated until all the K clusters are produced. And the algorithm for this bisecting K-means K-means is given here. Initially, the list of clusters to contain the cluster consisting of all points. That means here you need to initialize the list of clusters. What are the list of clusters? That's to be initialized. And remove a cluster from the list of clusters. This process must be repeated until the list of clusters contains only K clusters, and this must starting from 1 to the number of trials, you need to divide the cluster what you have considered into two clusters. Bisecting is nothing but dividing it into two parts, and select the two clusters from the bisection with the lowest SSA value and add it to the list of clusters. Among those two clusters, here you will be choosing only the cluster having the least SSC value, and this will be added to your list of clusters. This is about the bisecting K-means algorithm. And let us see what are the strengths and weaknesses of K-means algorithm. Here K-means is coming to the strengths of the K-means algorithm. It is a very simple algorithm and it can be used for a wide range of data types. Different data types can be applied, and it is a very efficient algorithm, though it will be executed for multiple runs. And coming to the bisecting K-means, it is also even more efficient. It is an extension of a K-means algorithm, and even then it is it is more efficient, and it is less susceptible to your initialization problems. These are the different strengths of the K-means algorithm. Coming to the weakness of the K-means algorithm, it cannot handle the clusters of different sizes. Suppose if you are considering the clusters having different densities and different sizes, that means one cluster will consist of only 2 data objects and the other clusters will consist of some 20 or 30 data objects. They are having different densities. The densities are not so nearer to each other. Such type of clusters cannot be handled perfectly by this K-means or either bisecting K-means algorithm. And the K-means algorithm also it is having a trouble clustering the data which contains outliers. Earlier we have discussed that outliers must be identified earlier. Otherwise, if you are having outliers, the problem is the total SSA value will be increased, and our main aim is to reduce the SSA value. Therefore, the outliers must be eliminated, and here the K-means is having the trouble of identifying the outliers, and K-means is restricted only to the data where the main prototype is the centroid value. Here these are the strengths and weaknesses of the K-means algorithm. This is about the basic K-means and bisecting K-means algorithm. Thank you.